Hi, my name is Lou Signorelli. I'm with the Electric Power Systems Integration Engineering team in Mossville, Illinois. Today I'm here to talk to you about UPS 101. Today we'll cover what are power interruptions, what is a UPS, and the different types of UPS systems. If at any time you have a question, you'll find a comment box located right beneath these slides. Please feel free to enter your question, and it'll automatically be sent to my email box, at which time I will do my best to return your email with an answer as soon as I possibly can. So, what are power interruptions? As we all know, poor power quality manifests itself in a variety of different ways. It can mean system downtime, create black screens, we can have systems lock up, we can have keyboards stop working. AT&T reported that close to 70% of all computer errors are caused by a power quality disturbance of one kind or another. When we think about the opportunities for poor power quality, it starts with transmission and distribution. And if you consider just in your own region the length or distance that power must travel from the power producer to the end user, it's amazing sometimes that we get power at all. But if you think about it, transmission lines may fail, flashovers from lightning, when you think about the vast terrain that these distribution systems must cover, voltage switches reclosing, disturbances caused by wind generators or anything else that may be using to supplement the initial power provider, cable failures, etc., right down to the squirrel that crawls into the local transformer or crawls into the local substation causing a short. So there's plenty of opportunity for disruption completely beyond our control. When you look at the load side, and that's the things that happen in our own buildings, we see lots of opportunity for things to cause interruptions or anomalies to our power. Think about working at home with a drill and you get static on the radio, or firing up a hairdryer and you see the result of that on your television set. Well, in our commercial buildings, our retail space, our industrial spaces, even our data centers, there's lots of ancillary loads that put noise and disturbances back into the system that the UPS must also be able to deal with. When we take a closer look at our power interruptions, we typically try to look at that from a graphic perspective. So here we see a sine wave coming into our facility, and lo and behold, there's a transmission line failure. So it goes flat. Well, when the line goes flat, we know the lights go out. Next, we talk about motors being introduced. And many facilities have motors that come on almost randomly throughout the building because of different manufacturing processes. When those motors come on, they absorb a great deal of current. As a result, we see a low voltage situation. Low voltage often manifests itself in the ways of, well, when the lights go kind of dim during the day. Typically, that means that something else is drinking up that voltage. High voltage? What about when people turn motors off? Or we see compressors that get turned off, and all of a sudden there's an extra availability of power. We will oftentimes see high voltage situations there. That can also happen when the utilities place extra capacity on the line, driving the voltage up almost instantaneously. Spikes often happen. The biggest culprit, of course, lightning. As a lightning strike happens near your house, many of us have lost electronic components. That's pretty normal. That's why we need TVSS, transient voltage surge suppression, as well as UPS in our facilities. Harmonics. These are noise. We measure these in a number of different ways, but typically harmonics, think of it like music. When you talk about thirds and fifths and chords and what have you, that's about like it works in electricity. So nonlinear loads, such as computers, are notorious for sending harmonics back through the system, and that's a load side example of what the UPS has to deal with many times. But when you combine all these together, you can see just why we need a UPS or some form of protection in our system so that our loads remain protected. The end result, of course, is the perfect wave. The optimum power condition, constant, clean power. So, let's talk about what is a UPS. A UPS is a piece of power electronics that lives between the input voltage and the output voltage. Pretty obvious, huh? But it gives us uptime, data safety, hardware protection, and in case you were wondering, UPS stands for uninterruptible power supply. So we want power electronics with a backup power supply that enables us to ride through these power anomalies as they occur to us throughout the day. When we look at how the UPS is installed, it is installed on the load side of an automatic transfer switch, or what we see there is represented as the input panel, and before our distribution panels or power distribution units or whatever else might be used to distribute the power downstream. So, what should we be considering when we talk about our UPS requirements? What we've listed on this screen are a variety of different critical components that are important as we consider UPSs. Load dissipation, constant uninterruptible clean power, low weight, low installation costs. These are things that are very important to customers as they're considering UPSs in their facilities. Why? Well, low heat dissipation means high efficiency. It means I, as a customer, can spend less on cooling or air conditioning in my data center. Constant uninterruptible power means that we want to select the right technology or topology for our UPS. We want to make sure that we've got backup power supplied via batteries, flywheels. We might want to consider putting a generator in this system as well so that the UPS could transfer gracefully to our genset for an extended runtime. Low weight is always important because we don't want to have to install reinforced floors or do something that's going to drive cost to our installation. We also like small-sized UPSs because we can then use the remaining square footage for profit-producing activities. Low installation costs. Why is that important? The less time a contractor has to spend on site installing a UPS, the less cost there is to a customer. So, let's talk about different types of UPS. We talk about passive standby, line interactive, and double conversion. These are terms that you'll hear tossed about quite freely when talking about UPSs. Let's see if I can shed some light on what they are. Passive standby. This is where the backup power is not directly connected to the main power path, or during normal operations you'll find it available but not connected. There's very little line conditioning going on in a standby UPS. These are great for under-the-desk, kind of at-home type of applications. Line interactive. Those of us in the UPS world are not very creative, so line interactive is exactly what the name says. It interacts with the main power path. So the backup power is always connected to the load, however not in the primary path. The power is conditioned typically through the use of filters and different types of active conditioning. So it's constantly adjusting the voltage and the sine wave to make it closer to perfect on the output side. Double conversion is exactly what the name implies. We're going to go through two conversions. We're going to take the normal incoming voltage, convert it from AC to DC, float charge our batteries, then convert it back from DC to AC, creating a perfect sine wave output via the inverter on the output. But that conversion is all happening in the normal power path. So let's see how that represents itself in our chart. The normal power path, as you can see from a passive standby perspective, flows through the input disconnect, through the filter, and out through the output switch. When faced with an output condition, we notice that now the output shown in the red line is provided from the battery through the inverter to the output switch. Let's look at line interactive for a moment. When you look at the normal power path, we show it through the normal power path via the static switch, the line inductor. If you look at the vertical line, we see the filter inductor. These two inductors provide most of the conditioning. We provide some power down to, in this case, our high-speed flywheel. It could also be a battery, thus keeping it at the high-speed flywheel, in this case, at its rated speed, waiting for any kind of a power anomaly to come along. And when it does, it takes over the load. In this case, the flywheel assumes the full load, passing our voltage from AC to DC through the first converter, from DC to AC through the second converter, and out to the load. While this is occurring, our gensets are firing and coming up to rated speed and voltage, at which time this UPS will walk in the genset to assume the full load presented to the UPS. In our double conversion lineup, as we mentioned a moment ago, the normal power path, as the name implies, falls through our rectifier charger, through our inverter, and to the output, putting a float charge on our batteries in the middle, and when presented with an outage, the batteries continue to supply that power to the inverter. No switching needed. That power from the batteries thus converted from DC to AC and presenting a perfect sine wave output to the load. So, offline, the UPS inverter connected in parallel with the AC input voltage. A switch must occur to get to the backup power. As we mentioned a moment ago, great for 5-6 minutes of backup for your PC at home or maybe your plasma TV at home. Great technology for that. Line interactive, a more active type of filtering. We find that the backup power is still connected in parallel, but it remains on and active at all times with the load, interacting, thus the term line interactive, with the load at all times. And online, some people use this interchangeably with double conversion. The UPS is with the inverter connected in series or in the main power path with the AC at all times. The inverter stays active all the time, converting that DC power back to AC and thus on to the load. So again, thank you very much for your time today. If you have any questions, please use that comment box. I look forward to your comments. Thank you.